Over the last few lectures, we have been taking a look at the theory of representations of Sn, the symmetric group of permutations of n objects. The major tool that we have used in the process has been a theorem due to Frobenius. And the theorem, in its simple form, goes as follows. Given a subgroup H of a group G, the numbers psi L, given by G over H times HL over GL, assigned to each class KL of G, provides a compound character for the group G. That is, provides the character for some representation of the group G, not necessarily an irreducible one. Here small g stands for the order of the group capital G. Small h, of course, is the order of the group capital H. GL is the number of elements in the Lth class, and HL is the number of those elements of the Lth class which survive into the subgroup capital H. We have been making use of this particular formula with special reference to Sn. In particular, for Sn, we have defined a subgroup H of lambda for each partition lambda of n. Now, let me remind you that a partition lambda of the integer n is a non-decreasing sequence of non-negative integers which add up to n. And given these integers lambda 1, lambda 2 all the way up to lambda n, what we have done is we have defined a subgroup of Sn which is isomorphic to the direct product of S lambda 1, S lambda 2 and so on up to S lambda n. The elements of this particular subgroup H of lambda permute the first lambda 1 objects among themselves, the next lambda 2 among themselves and so on. So each element of H lambda is of course a permutation of the n objects that Sn is permuting. Now, in the Frobenius formula, we need the numbers G, H, GL and HL. G, the order of the group Sn, is obviously n factorial. H is the order of this direct product group, which is of course the product of the orders of the individual groups which go into making it. So that's simply a lambda 1 factorial for S lambda 1 times lambda 2 factorial for S lambda 2 all the way up to lambda n factorial. So G and H are pretty easy to figure out. Now what about GL and HL? Now in GL we are looking at the number of elements in a particular class, and we have already learned earlier that the number of elements of a given class, which remember is characterized by a particular cycle structure, can be easily related to the numbers of the different cycles that are there. So if a particular class has a cycle structure given by 1 to the alpha, 2 to the beta, 3 to the gamma, which, let me remind you, simply means that it has alpha 1 cycles, beta 2 cycles, gamma 3 cycles and so on, then the number of elements in that class, GL, turns out to be simply n factorial divided by 1 to the alpha, alpha factorial, times 2 to the beta, beta factorial, times 2 to the gamma, gamma factorial and so on. Now this is the result which we had derived earlier. What we still need to figure out is HL, the number of these permutations which actually survive into our subgroup capital H of lambda. So what we need to do is figure out exactly how many of these permutations with alpha 1 cycles, beta 2 cycles, gamma 3 cycles and so on are elements of H of lambda, where only the first lambda 1 objects are permuted among themselves, the next lambda 2 are permuted among themselves and so on. So, any permutation which survives into this subgroup H, that is, any permutation which is in the intersection of this particular class of ours and the subgroup H, must have some of its 1 cycles, 2 cycles, 3 cycles from S lambda 1, another 1 from S lambda 2 and so on. So let's say it has alpha 1, 1 cycles, beta 1, 2 cycles, gamma 1, 3 cycles in S lambda 1. Similarly, alpha 2 of its 1 cycles, beta 2 of its 2 cycles, gamma 2 of its 3 cycles, etc. come from S lambda 2, and all the way down the line up to alpha n 1 cycles, beta n 2 cycles, gamma n 3 cycles and so on, coming from S lambda n. Now, these numbers alpha 1, alpha 2, beta 1, beta 2, etc. cannot be completely independent. There is one obvious condition, of course. The total number of one cycles which our permutation has is alpha. So the alpha 1, alpha 2, etc. must add up to alpha. Similarly, beta 1, beta 2 added up to beta n must be equal to beta, which is the total number of two cycles. And going on along these lines, gamma 1 plus gamma 2 up to gamma n must be equal to gamma, and so on. In addition to these constraints, there must be other constraints coming from the fact that S lambda 1 deals with permutations of exactly lambda 1 objects, which is why the total number of elements in S lambda 1, that is lambda 1 itself, must be equal to alpha 1, the total number of elements in the 1 cycles there, plus twice beta 1, the total number of elements in 2 cycles there, plus thrice gamma 1, and so on. And we have one such condition for each of our subpieces. Each lambda 1, lambda 2, lambda n must have a condition like this. So, for every set of non-negative integers, alpha 1, alpha 2, beta 1, beta 2, all the way up to alpha n, beta n, gamma 1, gamma n, and so on, which satisfy these conditions, we have a permutation which is actually in my subgroup capital H. The question is, how many such possibilities are there? Now, for every solution of these constraints, that is for fixed values of alpha 1 to alpha n, beta 1 to beta n, and so on, the number of permutations that we have is easy enough to figure out. The number of such permutations in S lambda 1 is simply lambda 1 factorial by 1 to the alpha 1 factorial times to the beta 1 factorial, and so on. Exactly the same formula that we used a while earlier to find out GL. Similarly, for each of these permutations in S lambda 1, there are this many permutations, lambda 2 factorial by 1 to the alpha 2 factorial, and so on, in S lambda 2, and so on all the way down the line. The product of all of these gives us the number of permutations corresponding to this particular solution, alpha 1 through alpha n, beta 1 through beta n, etc. of the constraints. So, for each such solution set, alpha 1, alpha 2, alpha 3, etc., the total number that gets contributed to the Frobenius formula is G, which is this quantity here, divided by H, divided by G lambda, which is this number, multiplied by this factor. This, by the way, is not H lambda or HL, simply because this is only the contribution for a particular solution set alpha 1, alpha 2, alpha n. We need to add this over all possible solutions to the constraints in order to get the final result that we need. That is the compound character for the class L as given by Frobenius' formula. But persisting with this piece for the time being, let's just notice that there is a lot of cancellations to be done here. Note that the n factorials simply cancel out. So do all these lambda 1, lambda 2, lambda n factorials with this denominator. Not only that, if you take the 1 to the alpha 1, 1 to the alpha 2, 1 to the alpha n, all of them together, you get 1 raised to the power alpha 1 plus alpha 2 up to alpha n, which according to our constraint is simply 1 to the alpha. Similarly, 2 to the beta cancels with 2 to the beta 1, 2 to the beta 2, 2 to the beta n, and so on. So all that survives ultimately for the contribution for this particular solution is alpha factorial times beta factorial times gamma factorial and so on, divided by alpha 1 factorial, alpha 2 factorial up to alpha n factorial, then beta 1 factorial, beta 2 factorial up to beta n factorial, and gamma 1 factorial, gamma 2 factorial up to gamma n factorial, and the rest. Of course, what we need to do is add over all solutions of the constraints to get the contribution that we want, that is G by H times HL by GL. And therefore, our compound character psi corresponding to the partition lambda in the class given by the cycle structure 1 to the alpha, 2 to the beta, etc. is given by the following formula. Is the sum over all solutions alpha 1, beta 1, alpha and beta n of these constraint equations of this quantity alpha factorial divided by alpha 1 factorial, alpha 2 factorial up to alpha n factorial, beta factorial divided by beta 1 factorial, beta 2 factorial up to beta n factorial, and other such terms. So what we have done is we have actually managed to reduce the Frobenius formula into a sort of closed form expression. However, because we have to add up over all solutions which satisfy these constraints, this is still not in as simple a form as we would have loved it to be. On the other hand, these factors that you can see on your screen right now, this, etc., are very easy to interpret. For example, this one is the number of ways in which alpha objects can be split up into groups of alpha 1, alpha 2 up to alpha n. This one is the number of ways in which beta objects can be split up into groups of beta 1, beta 2 up to beta n. And all such factors here actually have exactly the same interpretation. And if you remember your high school algebra, these would exactly be the coefficients that would sit in front of a multinomial expansion. That's a generalization of the binomial expansion, where instead of just squaring or cubing a plus b, you square and cube terms like x1 plus x2 plus x3 up to xn, or raise them to higher powers even. That is what we are going to exploit next to figure out an alternative way for the calculation of these compound characters. This will be a more efficient approach than the ones we have talked about before. But more importantly, they will also open up the route towards various proofs that we want to make, as well as further extensions of this approach, so that we in the end up with a prescription which gives us not the compound characters like this, but simple characters directly. We now make use of this fact that this factor is nothing but the coefficient of x1 to the alpha 1 times x2 to the alpha 2 up to xn to the alpha n in the expansion of the sum of all xi's with I running from 1 to n raised to the power alpha, and of course the other factors beta factorial by beta 1 factorial, beta 2 factorial up to beta n factorial has a similar connotation. We then go on to see that these constraint equations that we have will help us to demand that if we take this quantity, which is the sum of all the xi's raised to the power alpha, then the sum of all of their squares raised to the power beta, the sum of all their cubes raised to the power gamma, and so on, and look for the coefficient of x1 to the lambda 1, x2 to the lambda 2 up to xn to the lambda n here, what we are going to end up with is exactly the coefficients that we had called the compound characters earlier. Note that if x1 comes with a power of alpha 1 from this term, and the corresponding power here is beta 1, but not of x1 but of x1 square, and you have a power gamma 1 here, that is a power of 3 gamma 1 for x1. So ultimately, when you put them all together, you end up with the condition that alpha 1 plus 2 beta 1 plus 3 gamma 1 added up all together gives you lambda 1. And a similar thing can be stated about x2's powers, x3's powers, and so on. So this is essentially what you look at. You are looking at this particular combination of polynomials, and we want to read off the coefficients one by one, and that is going to give me the compound characters that we are talking about. Note that this expression is symmetric under the permutation of all the x's. So are these, and so that means so is the product. Therefore, in the product, say if you have x1 to the power 4 into x to the 3 into x2 to the power 1, we are also going to have another term with x1 to the 1, x to the 4, x3 to the power 3 with exactly the same coefficient. In other words, given one term like this, all terms which are obtained by permutations of the xi's from that one will come in with the same coefficient, so we can always group these things together. To make use of this, we define the symmetric polynomials. S1 is the sum of all xi's with I running from 1 to n Note that I have written down this as sum over all possible permutations of x1. What this really means is if you carry out all the possible permutations that are available, 1 will become 2, sometimes 1 will become 3, 1 will become 4, and all of these terms will be added together here. All the distinct terms that you get by permuting the labels 1, 2, 3 up to n will be sitting here. Similarly, S2 is the sum of all the x squares, and that I am going to write as xi square sum over all permutation. Once again, let me remind you, this is the sum over all the distinct results of the permutations of the symbols 1, 2, 3 up to n in this expression. In general, Si is simply going to be the sum of all the ith powers of x1, x2 all the way up to xn, and that can be written down as a sum over all possible permutations of x1 to the power I. You have to be a bit careful about the terminology here. I am saying that this is a sum over all permutations, but that is strictly speaking not really correct. I am not going to count the cases where the same thing occurs multiple number of times. After all, there are plenty of permutations which will leave, say, x1 unchanged. So, x1 will come not only once, but many times if you sum up over all possible permutations. We are not really doing that. We are only looking for distinct terms which come from permutations. So, essentially, x1, if it stays as x1, we don't count that once again. But in a permutation which changes it to x2, will give rise to a term x2 to the power I, and you are going to add that. Similarly, another permutation, in fact, quite a lot of them, will change x1 to x3. And that will give you x to the power I, but only once. Only the distinct terms. You don't count the number of times you get x3 out of x1. Having said that, what we are going to state is the following. The Frobenius character of the class 1 to the alpha, 2 to the beta, 3 to the gamma for the subgroup H lambda, which are found by invoking a partition lambda of n, is the following. It's nothing but the coefficient of x1 to the lambda 1 into x2 to the lambda 2 all the way up to xn to the lambda n in the expansion of s1 to the power alpha, s2 to the beta, s3 to the gamma. This is nothing but a restatement of what we have said a while ago. The important point is, if you want to write down s1 to the alpha, s2 to the beta, s3 to the gamma, and so on, and expand it completely out, you are going to get not only x1 to the lambda 1, x2 to the lambda 2 up to xn to the lambda n with a particular coefficient, but all terms that you get, all distinct terms that you get by permuting the symbols x1, x2 up to xn are also going to be there with exactly the same coefficient. That is, after all, a consequence of the permutation symmetry that this particular result has. Permuting the indices will not change the expression. So, for a given class L, which is defined by the cycle structure, alpha 1 cycles, beta 2 cycles, and so on, the corresponding symmetric polynomial S of L is going to be S1 raised to the power alpha, S2 raised to the beta, and so on, which is going to end up being a sum over all possible partitions of n, actually, of some number multiplying this sum over all distinct permutations of x1 to the lambda 1, x2 to the lambda 2 up to xn to the lambda n. And these coefficients are exactly what we are looking for. Just to illustrate what we mean, let me just show you a very simple calculation. For example, if you look at S1 square, which you will get if you have a class which has two 1 cycles, that is going to be simply x1 plus x2 up to xn whole square, and that, as you all know, is simply x1 square plus x2 square up to xn square plus twice x1 x2 plus twice x2 x3 and so on, all the way up to twice xn minus 1 xn. But if you write this using our notation, this is going to be nothing but sum over all permutations of x1 square, because distinct permutations are going to give me x1 square to begin with, then x2 square, then x3 square up to all the way up to xn square. And then this one we are going to write as x1 x2 multiplied by 2 summed over all possible permutations. Again, only distinct polynomials that you get from permutations. So when you permute 1, 2, 3 up to n, some permutations will of course leave x1, x2 the same, but others will change the indices 1 and 2, let's say to 1 and 3, so you get x1, x3, you will also get x2, x3, x1, xn and so on. All of these permutations are going to be added to this, which is of course exactly what this really says. Now, before we go on to do more serious computation of various symmetric polynomials, let me just illustrate how to recalculate this using our notation and our notation only. S1, remember, is the sum over all permutations of x1, and you are actually multiplying it with itself. Now, the way in which we can do this without expanding this whole thing out is the following. There will be terms here that you will get by multiplying x1 with x1 itself. So, you will get terms like x1 squared. And of course, because of the permutation symmetry this has, all possible permutations of this will also come in. So, this is one term that you get. Another term that you will get is when you take x1 from here and x2 from here, you will get x1, x2. Of course, because of the permutation symmetry, all possible distinct permutations will also be counted. But now you have to be careful. In how many ways can you get the exact term x1, x2? That you can get by taking x1 from here and x2 from here. You can also get that by taking x2 from here and x1 from here. So this actually comes in twice because a given term like x1, x2 specifically comes twice. One with x1 from here, x2 from here, the other with x2 from here, x1 from here. Well, any other permutation also works the same way. Say one of these permuted terms will be x5, x6 if you are using that many variables. Then that will come by taking x5 from here and x6 from here, or by taking x6 from here, x5 from here. Two distinct ways of doing this, so you will get twice x5, x6. Of course, I am not writing twice x5, x6 separately because that's taken care of by this permutation symbol. So this is what S1 square really turns out to be. We will now make use of this basic idea to calculate various different symmetric polynomials for different classes and try to use this to form all the compound characters, say for S7. Once again, why S7 and not anything else? Simply because in earlier lectures, we have actually worked out the character tables of all the Sn's up to S6. So S7 is the next one in line. As a first step, let us begin by listing down all the partitions of the number 7 and the corresponding terms that you will see here because of those. So 7 has the following partitions. 7 itself, of course this corresponds to x1 to the 7 and all its permutations. I'm not just not writing down all the permutations. Then you have 6 plus 1. This corresponds to x1 to the 6, x2 plus permutations of course. Then 5 plus 2, x1 to the 5, x2 square, x1 to the 5, x2, x3, x1 to the 4, x2 cube. I think you can spot the order here rather easily. All we are doing is we are decreasing the extreme, the rightmost number here to the lowest value it can go, and then starting all over again with the largest value you can have for the leftmost number, then the largest possible value here, and so on. So now, for example, in the next step, I'm going to decrease the 3 here and make that 2, adding, of course, one more term to the next. So get x1 to the 4, x2 cube, x3. Of course, 1 cannot be decreased any further, or even if it is, that would really not give you anything new. So you don't bother decreasing this, but you decrease the 2 and it becomes 1 plus 1 plus 1. So you get x1 to the 4, x2, x3, x4 as a term on the right hand side of our formula. And we can go on and on and on and write down for all the 15 partitions. Now these partitions get a bit confusing to read as you go further and further down, especially because there are way too many terms. So this notation It's just a compact version for this. So instead of 7, you just say 7, nothing new. But for example, instead of this, you say 3, 1 to the 4. Now, an added advantage of this is that this also gives you all possible cycle structures for permutations in S7. For example, this notation, when you're talking about a class, it will stand for a class with 7 1 cycles. This one will stand for a class with 1 2 cycle and 5 1 cycles and so on. So all the 15 possible classes have also been represented here. Let me give you a small word of warning here. The connection between partitions and cycle structures that we talked about earlier is actually just the opposite of the one I'm noting down here. For example, this would mean a partition with lambda 1 equals 7, lambda 2 equals 0, in fact all other lambdas equal to 0. And this would actually give you nu 1 equals 7, that is 7 1 cycles. That actually corresponds to this class here. On the other hand, this one, in this language, this particular partition would have corresponded to 0 1 cycles, 1 minus 1, 0 2 cycles, 0 3 cycles, 0 4 cycles, 0 5 cycles, 0 6 cycles, and exactly 1 7 cycle, which in our cycle notation would stay here. So our labeling of classes and labeling of partitions are in a way complementary to each other. But you can use any one of them to label either the classes or the partitions. Let's just not get confused between the connection of the two. In fact, you will see that when we write this in tabular form, we are going to label the classes with 1 to the 7 coming first, 2 1 to the 5 coming after that, and so on. So we will go this way, from right to left, so to speak. But when we label the partitions on the right hand side of our expression, we are going to go this way. I think this is more confusing when I say it than it really is. So let us just go and take a look at exactly what we are going to do. The first class that we are going to look at is the class with 7 1 cycles, 1 to the 7. And of course, its corresponding symmetric polynomial is S1 to the 7. That is what we need to calculate to begin with. However, getting to S1 to the 7 in one go is a big leap. So what we will do is we will do it in steps. We already know S1, of course, is this, and S1 square we have figured out a while ago is this. To get to S1 cube from there, you need to multiply this expression by S1, which is of course sum over P. I've written X3 here, I could have written Xi for any I. The sum over permutations take care of that. Now to go on to the next step, what I need to do is see exactly how many ways can I combine this with this. I can of course get an x1 cube term by taking x1 square from here and x1 from here. Remember this, although I've written x3 here, this is a sum over all possible permutations. So x1 is of course definitely a term here. So I'll get x1 cube, and you should be able to convince yourselves that that's the only way you're going to get x1 cube, by taking an x1 square from here and an x1 from here. Of course, you will also get x2 cube and so on, and that's taken care of by the permutation sign. But you'll get only one x1 cube, so the coefficient in front of that is 1. The next term you're going to look at is the next partition of 3. So 3 here, of course, is 3. Then the next partition is 2 plus 1. So x1 square x2, that's the kind of term I'm going to look at. Now, how do you get x1 square x2? You get it by taking x1, x2 from here and x1 from here. That gives you x1 square x2, but of course, since here you already have a coefficient of 2, you will get twice x1 square x2 in that manner. But that is not the only way in which you can get x1 square x2. You can also get it by taking x1 square from here and x2 from here. So that is why that gives you an additional x1 square x2. So x1 square x2 in particular comes with a coefficient of 3. Of course, you will have all other permutations like x2 squared, x5 and so on as well. But all of them will come with a coefficient of 3. Finally, you will have a term which corresponds to the partition 1 plus 1 plus 1 of 3, which of course is, in terms of polynomials, x1, x2, x3, summed over all its possible permutations. Now let us take a look at how you can get x1, x2, x3, and in particular, how do we arrive at this coefficient 6. In how many ways can you get this particular element x1, x2, x3? Forget about its permutations. Just x1, x2, x3. You can get it by taking x1, x2 from here and x3 from here. That's one possibility. That would have given you a factor of 2. But you can also get it by picking x1, x3 from here and x2 from here. You could also get this by picking x2, x3 from here and x1 from here. So there are 3 distinct ways you can get this particular term x1, x2, x3, each of which gives you a coefficient of 2, and therefore the overall coefficient is 6. If you are a bit confused with this, I would suggest that you write down x1 plus x2 plus x3 whole cube and multiply it out. But anyway, multiplying things out completely can work for the lower order polynomials, but will get tougher and tougher as you go along. So please try to understand exactly what we are doing here. We are just focusing on one of these terms, especially the one which we are writing down here, and seeing how many ways we can get that one. All the possible permutations will have to be there because of the symmetry of this polynomial and their products anyway. Okay, let's quickly work out s1 to the 4 using the same argument. And I'm not writing down the steps here, I've just written down the answer, but let's try to understand where this comes from. Remember, for s1 to the 4, you need to multiply this expression by sum over all permutations of, let's say, x1. And therefore, you can get x1 to the 4 in only one way. Take x1 cube from here and x1 from here. That's why you get a coefficient of 1 here. Next term, the next partition of 4 is 3, 1. x1 cube x2 is a typical term in that. And how can I get specifically x1 cube x2? I can get it by multiplying x1 cube from here and x2 from here. That will give you a coefficient of 1. But you can also get it by multiplying x1 square x2 from here and x1 from here. That will give you an overall coefficient of 3. So taking both possibilities together, you get a coefficient of 4. What about the next partition? 2 plus 2, x1 square x2 square, being the typical term. Now you can get that by taking x1 square x2 from here and x2 from here. But you can also get it by multiplying x1 x2 square from here, which is also there in this particular permuter sum, and taking x1 from here. So there are 2 different ways of arriving here that will give you a 6. In fact, this 2 is easy to understand. This final result that we have has x1 and x2 at exactly the same status. So whatever you will get using an x1 from this side, you will be able to get that also by using an x2 from this one. And that's why this 6, 3 essentially gets doubled. Now let's look at x1 square, x2, x3. How do we get that? We can get that by, of course, starting from x1, x2 to x3 here and multiplying it by x1. Coefficient of 6. This 6 times this 1. But that's not the only way. You can get it by multiplying x1 square, x2 here by an x3. So that gives me an additional factor of 3. But notice that x2, x3 has the same powers here. And that actually indicates that not only can you get this by multiplying x1 square, x2 by x3, you can also get it by multiplying x1 square, x3, which is in this sum, by x2 from here. So this 3 times 1 actually gets doubled to 6. And that adds to the 6 that you already have. So the coefficient in front of x1 square, x2, x3 is 12. Finally, x1, x2, x3, x4. In how many ways can you form that? One way, of course, is taking x1, x2, x3 as you can see from here and x4 from here. But that's just one way. In fact, the final term that you need to complete this quartet can be either x4 from here or x3 or x2 or x1. And the other 3 can come from here. So there are 4 distinct ways of getting specifically x1, x2, x3, x4. Each time you have a coefficient of 6. And therefore, the overall coefficient is 24. With some practice, this will be a very, very easy thing too. So let's quickly continue to x1 to the 5. x1 to the 5 can be obtained by multiplying this x1 to the 4 by x1. Coefficient of 1. x1 to the 4 x2, the next partition. From x1 cube x2 times x1 or x1 to the 4 times x2. 4 from the first option, 1 from the second. So that's a 5. x1 cube x2 square can be obtained by multiplying x1 cube x2 by x2 or x1 square x2 square by x1. 4 from the first, 6 from the other. That's 10. x1 cube x2 x3. Well, you can get this by starting from x1 square x2 x3 and multiplying by x1. That gives you 12. Or you can start with x1 cube x2 from this with x3 from the other one. Or x1 cube x3 from here and x2 from the other one. Again, equal powers on x2 and x3 tell you that you can actually do this in two different ways. And that's why this 4 gets doubled, becomes 8, and then adds with the 12 we already have to get 20. Why is this 30? Quickly, x1 square x2 x3 in the origin, in the s1 to the 4 came with 12. But that can come in twice. Once as x1 square x2 x3 times x2, again as x1 x2 square x3 multiplied by x1. So that's 24, and the final one is you can take with x1 square x2 here, multiply by x3. That can only be done in one way, and that gives you another factor of 6. So 30 overall. This 60 simply comes from x1, x2, x3, x4. This one, that's 24. And x1 square x2, x3, which is here, that would have given you 12, but it can give you 12 in 3 different ways. You can either take x2 from the second factor or x3 or x4. So that's an overall 36, and 24 gives you 60. And this one, 24 every time, but the one element that you get from the second sum could be x5, x4, x3, x2 or x1. 5 different ways. So 120. Proceeding this way, we can easily write down s1 to the 6. I'm not going to tell you in detail how this comes about, but you should be able to figure it out yourself. And s1 to the 7. A pretty lengthy expression, but once again, something which can be figured out very, very simply. Now, you might have, of course, thought of another approach. Instead of going from s1 to the power 1 to s1 to the 7 in steps like this, you could have calculated s1 square first, then squared that to get s1 to the 4. Multiplied s1 to the 4, s1 to the 2 and s1 to the 1 to get s1 to the 7. That would definitely lead to lesser number of multiplications, but maybe slightly more complicated ones in each step. However, the reason why we did not do that is A, multiplying by s1 at every step is much simpler, and B, these intermediate results of s1 to the 6, s1 to the 5, etc. will also be needed when we talk of the other classes. Remember, this time we were talking of the class 1 to the 7, that is 7 1 cycles. So our symmetric polynomial for that class is 1 to the 7. However, for the next class, for example, the class which has 1 2 cycles and 5 1 cycles, what I will need is s1 to the 5 times s2. And so, for that, I would have needed the s1 to the 5, which we have calculated on the way. By the way, from the expression for s1 to the 7, you can already see some values of the compound characters pertaining to each and every one of the partitions. Since we are going to write down the classes along the column headers, so one column per every class, and the partitions label different representations. So partitions are going to be rows of my compound character table. These numbers 1, 7, 21, 42, 35, 105, 210, 140, 210 again, 420, 840, 630, 1260, 2520 and 5040. They will all form the very first column of my compound character table. As I have said a while ago, to figure out the next column of our compound character table, we need to find out the symmetric polynomial s1 to the 5 times s2. Now s1 to the 5 is something we had already figured out a while ago. This thing in the bracket here is s1 to the 5, and you have to multiply it by s2, which is the sum of x1 square and all its permutations. x1 square plus x2 square up to xn square. So the way in which we calculate the expression is essentially the same as what we have done a while ago. But there are some subtleties involved simply because here you're not multiplying by sigma of xi, but by sigma of xi square. So, for example, the first term is obviously x1 to the 5 taken from here and x1 square taken from here, giving you x1 to the 7 with a coefficient of 1. The next term, or the next partition, 6 plus 1, corresponds to the polynomials of the form x1 to the 6 x2. This particular expression x1 to the 6 x2 can be formed only by taking x1 to the 4 x2 from here and x1 square from here. There is no other option, and that's why this coefficient of 5 comes in here as it is. I have not written sum over all permutations here. I am just assuming that that's a given. It just helps to declutter the notation a bit. Now the next term, x1 to the 5 x2 square, can be obtained by multiplying this term here by x1 square. That contributes a factor of 10, this 10. You can also get the same thing by taking x1 to the 5 from the bracket here, from x1 to the 5, and multiplying it by x2 square coming from here. So the two together give you the 11. The 20 here, well, that's basically because you can form this by taking x1 cube x2 x3 from here and multiplying that by x1 square. There's only one way to get to that, and that's why you have a factor of 20. x1 to the 4 x2 cube can be obtained from x1 square x2 cube, which you can't see here directly, but that's actually there in one of the permutations of this term. So that gives you a 10. And the other term, of course, is x1 to the 4 x2 times x2 square, and x1 to the 4 x2 is here with a factor of 5. So now you have a coefficient of 15 in all. Proceeding in this manner, you can calculate the entire expression rather easily. And one important thing, it is rather trivial at this stage, but will turn out to be quite useful as you go along, is that you do not have any term of the form x1, x2, x3, x4, x5, x6, x7, simply because you're multiplying by at least a power of 2 here. So no term without powers of 2 can actually survive. Now this actually allows you to read off the second column of the compound character table immediately. It is going to be 1, 5, 11, 20, 15, 35, 60, 40 and so on down the column. 15 such entries, the last one of course being 0. Now I am not going to show you how to calculate each and every one of these polynomials for each class, simply because there are 15 of them and it's going to take a long time to work through all of them one by one. But it might be important to point out that as you go further and further down the line, for example, when you're looking at a class consisting of 2 cycles and 1 3 cycle, and hence corresponding to the symmetric polynomial s2 square s3, this is what you need to do. You need to square s2, and calculating the square of s2 does not require you to work the entire thing out again. You know s1 square. In the expression for s1 square, replace each xi by xi square. So s1 square had x1 square plus twice sum over x1 x2. s2 square will have x1 square, that's x1 to the 4, plus twice sum over x1 square x2 square. Of course, sum over all permutations being implied here. And then you have to multiply by s3, which is x1 cube. Now, although this looks like a rather lengthy thing to calculate, you should realize that there are only very few non-zero terms here. You can get x1 to the 7 by multiplying x1 to the 4 from here by x1 cube from here. You can get x1 to the 4 x2 cube by multiplying x1 to the 4 from here by x2 cube from here. That's one more term. And by multiplying this by x1 cubed, we can get x1 to the 5 x2 square, which is coming with a quotient of 2. And one more term, you can get x1 square x2 square times x3 cube, or by rearranging them you can also get x1 cube times x2 square x3 square here, in only one way, by the way, just by multiplying this term x2 square x3 square from here by x1 cube from here, and that comes with a factor of 2. And that is all. All the other terms come with coefficients of 0. So this particular column will be mostly zeros. Especially the bottom ones, as you write down the partitions, these longer partitions the ones with bigger pieces come near the bottom, and they will all be 0. And the reason why they are 0 is pretty easy to understand. You are multiplying by sum of cubes here, which means any term which is less than a cube, say these will definitely have to be 0. That these are also 0 follow from the fact that you do not have corresponding terms. You don't have an x2, x3, x4, x5 for example here, so that you cannot get this by multiplying by x1 cube. But anything which has all its powers below 3 definitely will have 0 coefficient. And going along this way, you can get more and more of the terms and work out all the 15 that I've done here. But I'm not going to go through all of them as I said. It takes a bit of care to work all of them out, but it doesn't really require a lot of complicated reasoning. It's just simple grunt work, which by the way can be done rather nicely by a machine. Anyway, after you calculate all of these things through, you are going to get this 15 by 15 table for compound characters. And as promised, most of these elements, at least the elements down here, are all 0. So frankly, though it looks like a huge calculation, it really isn't that big a deal. Many of these steps are trivially 0. But what is very important in this compound character table is the following. The very first line, as you can easily see, has to be a simple character. After all, it's a one-dimensional representation. And a very well-known one-dimensional representation. That's the identity representation, which by virtue of being one-dimensional has to be irreducible. This next representation that you can see is reducible. If you dot the character vector with itself, you are going to get 2, which essentially means that it has 2 simple characters occurring once each. One of them happens to be the one you have already found out. That's the one. So if you take this simple character, chi7, which is actually chi of 7, a simple character, from this compound character chi6, 1, you are going to get your next simple character, something which can label chi 6 of 1. And that will be 6, 4, 2, 0, 3, 1, minus 1, 0, 2, 0, minus 1, 1, minus 1, 0, minus 1. Can easily check that that actually is a simple character. Although as I said before, that should be sort of obvious from the way we have arrived at it. As you would definitely agree, working out the simple characters from this big 15 by 15 table is quite a lot of hard work, especially if you have to do it by hand. However, this very simple program that I have written for you can help you figure this out in almost a matter of seconds. Well, not really. The effort primarily here is in entering the compound character table. So I've used NumPy. Once again, if you do not know NumPy, don't worry, you can understand what's going on by just following the code. Here what we have done is built up a 15 by 15 array in which I have entered all these numbers. So the very first or the 0th row, in Python counting starts from 0, is just a bunch of ones. That's what np.ones 15 gives you. It gives you 15 ones in an array which I am storing in the 0th row of this 15 by 15 array. The 1th row, well, I've just put in the numbers, and all I've done is essentially replace the zeros that I had started with initially by those non-zero numbers that we have. And finally, this is how we just enter our entire compound character table. There could be other more efficient or more direct ways of doing this, but this is a reasonably good way to enter the entire array into my computer. After that, what I have done is primarily this. This is n's, which just is a 15 by 1 array, a one-dimensional array of 15 numbers, and these numbers are nothing but the sizes of each one of the classes that we have. Again, the size of a class can be easily determined by the formula that we have in terms of the cycle structure, and that's all we have used here to put in the numbers. And then the entire job essentially is done here. So what we do is we go through the rows of our compound character table one by one. We start at row number 1, not row number 0, because the row number 0 I already know is a simple character. We start after that. And what we do, apart from these print statements which you can ignore for the time being, is we run a loop of all the rows before that. So j in range I, for I equals 5 for example, j will go from 0, 1, 2, 3, 4. So I am looking at row number 5, but in row number 5 I have a compound character which is built out of simple characters which come before that. And my method is such that the previous 4 rows which started out as compound characters maybe have already been reduced to simple characters by the time I get to this. And all this does is finds out how many times the simple character in the jth row occurs in the compound character in the ith row by essentially calculating the dot product directly. Prints out that number just for our reference and then subtracts that jth row, which is of course the jth simple character, out nj times from the ith compound character. So it takes away all the occurrences of the jth simple character from the ith compound character. Finally, this will leave us with a simple character at the end. And just to see how this works, let me just run this program. So the program has run completely. Okay, just to go back to the beginning of this. It says when you are looking at I equal to 1, that is the 1th row, which is of course the second row of the compound character table. That was a compound character in which the row j0 occurred once, you take it away. And then you are left with a simple character. In this next row, the 0th simple character occurs once. The 1th simple character which you get after you take away chi0 from chi1 is occurring once. You take both of them away, you get the simple character and so on. Finally, this is the result that you get. Our compound character table has been changed into a table of simple characters. You can easily check that each one of these rows correspond to a 15 element simple character vector for S7. So we have now made use of the symmetric polynomials to figure out first a compound character table for S7 and from that a simple character table for S7, the proper character table. However, as we stated at the beginning, the use of symmetric polynomials is not just in calculating the characters, but in proving several important results. One of them is the guarantee that we talked about, which we have seen at work here, that using Frobenius' simple theorem, we should be able to get enough independent compound characters so that all the simple characters can be found from that. That we have managed to do it for S7 is something you can see on your screens right now. However, the proof that it can always be done hinges on some rather well-known results of analysis, which we are now going to show. First of all, we established that these SIs, which we defined, sum of all the ith powers of the x's, x1 to the I plus x2 to the power I plus all the way up to xn to the power I, these are actually functionally independent of each other. To prove that they are functionally independent, what we need to do is determine their Jacobian, and for that we need the partial derivative del si del xj. It's pretty easy to figure out that that partial derivative is I xj to the power I minus 1. Now the reason why we need this partial derivative is the following. We need to calculate the Jacobian of the map which takes the independent variables x1 through xn to this new bunch of n variables s1 through sn. And that Jacobian is simply nothing but the determinant of the matrix formed by these partial derivatives. So this Jacobian has the following structure. It has 1, 1, 1, 1. Then you have 2x1, 2x2, 2x3, 2x4, 3x1 square, 3x2 square, and so on, all the way down to nx1 to the n minus 1, nx2 to the power n minus 1, nx3 to the power n minus 1, and so on. Now the first row has 1 as a common factor. You can pull that out. From the second row, you can pull out a factor of 2. From the third, you can pull out a factor of 3, and so on. Going all the way down the line, you can actually pull out a factor of n factorial, 1 times 2 times 3, all the way up to n. And that leaves us with this simple determinant, where each row essentially are powers of the xi's. Now, the simple form for this determinant allows us to easily evaluate what that determinant is. It's an elementary exercise essentially in class 12 mathematics, and can easily figure out that this polynomial happens to be this particular product of all the xi minus xj factors taken in a particular order. You have avoided repetition by demanding that I is less than j in the product of all xi minus xj. That this is the correct value for the determinant can be easily seen by first of all figuring out what degree of polynomial we have, then noticing that if any two of these variables were to match, say x1 with x3, then two columns of this determinant will become identical. So x1 minus x3, for example, must be a factor. Similarly, x1 minus x7, x2 minus x5, all of these must be factors. The overall factor of this, that is just n factorial and nothing else, can be decided by focusing on any one of the particular terms that you get and seeing that the coefficient of that is actually 1 or minus 1 as the case may be. Now, the important thing is that this Jacobian is not identically 0. And that tells us that the functions s1, s2, s3 up to sn are functionally independent. Instead of using the original variable x1 through xn, you could also use s1 through sn as your independent variables. Now, next comes the point that SL, which are formed by powers of these s1, s2, etc., they must be linearly independent of each other. Because if they were not linearly independent, these s for each partition, then their dependence would ultimately boil down to a functional dependence in the set s1, s2 up to sn. So these have to be linearly independent. It's very easy to see that the pieces that we have found out on the right hand side of our expression, sum over a given partition lambda 1, lambda 2, lambda n of the quantity x1 to the lambda 1, x2 to the lambda 2 up to xn to the lambda n, summed up with all possible permutations of 1 to n. In those terms, they are also linearly independent variables. And that means that the expression that we had of S for a given class, S of L, S1 to the alpha, S to the beta and so on, being expressed as a linear combination of x1 to the lambda 1, x2 to the lambda, xn to the lambda n, summed up over all possible permutations. As this expression runs over all the nc classes of Sn, you get one such expression for each class. What we expect are nc quantities S of L in terms of the nc independent variables x1 to the lambda 1 up to xn to the lambda n. And since the SLs are all linearly independent, what we have here is a transformation from one bunch of linearly independent variables x1 to the lambda 1, xn to the lambda n's, summed over permutations, to another bunch, the S for a given class. Now, since this is a transformation from one linearly independent set to another, the matrix of this transformation must be non-singular, and the columns of this matrix, which end up becoming the rows of our compound character table, must then be linearly independent. Since you have nc linearly independent vectors, which are all combinations of the nc simple characters, the nc simple characters must be expressible as linear combinations of the Xi lambdas. This gives us a full justification of our statement that from the compound characters we calculate using Frobenius' method, and these partition-based subgroups, we should always be able to figure out the simple characters. Now, the utility of the symmetric polynomials does not end here. This approach that we have taken so far only allows us to calculate the simple characters in a roundabout fashion. You first calculate the compound characters and then eliminate simple characters within those compound characters to ultimately arrive at a final expression for the simple characters. However, as we will soon see, we can make use of these symmetric polynomials and a completely antisymmetric object, which is essentially the determinant of the kind that we saw a while ago, and use the two together to find a formula which will directly give us the simple characters. It is this that will ultimately lead us to the Young tableau approach for calculating the character table for Sn. But that is, of course, for the next lecture.